Dear colleagues, let me present a paper devoted to the problem of mathematical modeling of COVID-19 pandemic and its impact on economy. Infectious diseases rank first among the high risks that will affect the next decade. The global change have so intertwined sustainable economic development, food security, and public health that the global COVID pandemic has led to complex and far-reaching threats, not only in the medical field, but also in the economic, food, and social spheres. Epidemic control measures have become a heavy burden of the economy. Formulating effective strategies to normalize the economic situation during a pandemic, many governments face a difficult problem: how to support the economy in the short term while avoiding undesirable inflationary consequences and risks that could threaten financial stability in the medium term. The uniqueness of the COVID virus leads to a simulation of uncertainty, required special mathematical method used to study unlikely or unique events when the stochastic nature of the object under study or the incompleteness of the sample reduces the effectiveness of traditional statistical methods. In this regard, the development of models that take into account the influence of random disturbances, which increase the overall level of uncertainty, becomes particularly relevant. This model should also consider both epidemiological and economic factors and allow for the identification of effective strategies to minimize the number of casualties and economic losses from the epidemic under various scenarios of its development. The aim of this work is to develop such mathematical models to study the negative impact of global pandemics on economic development. The model of mutual influence between the pandemic and the economy should include economic and epidemic blocks and a system of relationships between them. In developing the economical block, we will utilize an approach proposed in our previous work when studying the interrelations of water, food, energy resources, food transportation, and medical consequences of the pandemic using a multisectoral Lorentz model. This model integrates equally described sectors of the economy into a unified structure, with each sector considered in terms of productivity, employment, and structural disruptions levels. The model allowed for identifying conditions for the occurrence of deterministic chaos and calculating trajectories of change in social economic factors to reduce the number of structural disruptions. This is achieved by changing the balance between demand and supply in the respective sectors of the economy. The study of this model allowed tracing how changes in this balance lead to the emergence of a chaotic, stable attractor. In developing the epidemic block, we will use a modification of models that are often used to study the spread of COVID-19. Typically, they describe the interaction of three population groups: susceptible, infected, and recovered, known as the SEER model. To investigate the relationship between changes in the economy and the epidemic processes, we will combine these two approaches. This allows linking the SEER model with parameters whose dynamics are determined using a model of the economic bloc. Let X, Y, and Z be normalized level of productivity, employment quantity, and structural disruptions, respectively, for the food production system, food transportation, and the medical sphere. We will use the following postulates. There is competition for labor between different sectors of the economy. Variability of crop yields, fluctuation in energy prices, change in the productivity of jobs introduced random disturbances W becoming additional factors increasing the level of structural disruptions. Processes in different economic sectors can occur at different speeds, and time scaling for sectors is accomplished using parameters epsilon. The model has the following form, where delta perturbation intensities, sigma RB parameters of Lorentz model, A parameters that characterize competition in labor markets, W independent standard Wiener process with following parameters. Investigating the canonical Lorentz model reveals that increasing the parameters R is critical for the emergence of both periodic and turbulent trajectories. Since in model 1 R are functions of the variable x, in fact we have a Lorentz model with variable parameters R. Threats to food resources belong to the category of long-term risks. For them, the value epsilon equal 1 is chosen. Disruption of transport chains and the medical sphere represent medium-term risks. For them, the value epsilon equal 2.5 is chosen. The weights A were chosen depending on the influence of the corresponding threat factor. The parameters sigma R, B are related to the characteristic that determine the functioning of economic sector as follows. For the study of the epidemic process, we will use the modified SER model, which has the following form, where Y1 susceptible individuals, Y2 infected patients, Y3 recurrent patients, Y4 deceased patients. Beta disturbance intensity parameters. W has the same meaning as it had in Model 1 and correspond to the same conditions. A0, the fraction of infected individuals who died, and total populations, T-inf, the active period during which the infected individuals is contagious, Tm, average recovery period of an infected individuals. We will consider that the reproduction rate depends on the effectiveness of the medical system's operation and is determined by the function R. We will also assume that the recovery rate depends on the productivity level of the medical system, which is determined by the function U1. The dynamics of variable x3 and z3 are calculated using model 1. The negative impact of the epidemic on economic processes will be investigated by replacing the parameter R in 2 with function R U2. An increase in the number of infected individuals will increase the parameters R into, and when they reach bifurcation values, this will lead to the emergence of stochastic regimes. Let us functions R, U1, and U2 have the following form. There are several bifurcation values of the parameter R, upon reaching which the system changes its operating mode and ends up in a regime of metastable chaos, resulting in the emergence of the estranged attractor. In Figure 4, it is shown how the increase in the parameter L3, which characterizes the level of impact of the pandemic on the functioning of the medical sector, contributes to the emergence of stochastic regimes. At L3 equal 850 and L3 equal 1000, cyclic oscillation begin, which dampen when the level of infected individual decreases to the level that was before the beginning of the epidemic. At L3 equal 1250 and L3 equal 1500, stable chaotic oscillation arises. In Figure 5, the results of modeling changes in the levels of disruptions in the food production system, food transportation, and medical infrastructure during the epidemic are shown. When modeling, the total population was chosen to be 34 million people. An increase in the parameters R leads to an increase in the number of infected individuals. Periodic trajectories are replaced by chaotic ones upon reaching the bifurcation value of this parameter. Figure 6 presents the results of modeling with variations of parameter B. The increase in these parameters simulates a decrease in job supply levels. We consider the case where the parameters are equal to each other. The growth of B leads to a significant change in the phase portrait of the system, resulting in a reduction in the levels of the structural disruptions in various sectors of the economy and a decrease in the peak number of infected individuals. With B growing, the overall number of infected individuals initially decreases and then begins to rise again. Identification of model parameters was carried out using World Health Organization dashboard data. According to this data, the peak of the epidemic in Ukraine was reached after 3 months, with the number of deaths reaching about 100,000 after 5 months, when the epidemic subsided. The total number of infected individuals was over 3.5 million. This data align well with the results of the pandemic development modeling in Ukraine conducted in this study. One of the most serious complications of COVID is an excessive immune response in which the level of pro-inflammatory cytokines responsible for regulating intracellular and intersystemic interactions sharply increases. This leads to the disruption of the immune system, an increase in the level of free radicals, causing multiple damage to internal organs, and alters the balance of synthesis and expenditure of energy in cell, posing a lethal risk. Unfortunately, the specific mechanism of the cytokine storm remains undefined, making research on the impact of the immune system on the course of COVID highly relevant. In modeling the epidemic processes, the key parameters that determine the dynamics of epidemics typically include the average values of the incubation period of disease, the active period when the patient is contagious, the recovery period, the time until death. It is important to note that these constants in epidemiological models are functions of the state of the patient's immune system, which plays a crucial role in fighting infection. However, there are currently no epidemiological models that allow for the consideration of the influence of the immune system state on the course of the disease and the selection of therapy. Therefore, the task arises to develop a mathematical model of immune cytokine storm. In mathematical modeling of the immune system response to antigenic determinants, typically the components facilitating antigen presentation, its destruction, regulation of proliferative processes, and modulation of the immune response are considered. This include helper, killer, macrophage, and suppressor cells. Tissue damage results in an energy imbalance, disrupting the interrelationships between energy function and mitochondrial activity for energy synthesis in the cell. A significant indicator of the imbalance, which increases with infection growth, is the number of structural disruptions in the cell energy system. Figure 8 shows how the dynamics of the immune response changed when the initial number of virus increases. The results of the modeling for the case where the virus infects macrophages are shown in figure 9 and 10. Parameters A28 characterizes the simulation of virus reproduction by infected macrophages. As seen from figure 9, when the value of parameter A28 reaches 0.07, the overall quantities of viruses, lymphoid factors, inflammation, and disruption sharply increase. As seen from this figure, the system is sensitive to small changes in parameters A28 in the following interval. If we consider the variables of model as the mean values across a selected population, then the indicator of the number of structural disruptions could characterize the collective immunity of this population. It is possible to examine the dependence of the parameters of model 3 on disruptions. The relationship between model 3 and 5 will be defined through the parameters A0, Tinf, Tm. Parameters K1 and K2 from model 4 also may be examined as function of disruptions. This will be considered in the further development of this work. The scientific novelty of the work lies in the following. A proposed approach to the development of complex systems based on the use of multi-sector Lorentz models, allowing the exploration of interrelationships between the state of economy and its dynamics of epidemic. The development of mathematical model that accounts for the role of herd immunity in the dynamics of pandemic spread. The developed models consider the superposition of two types of random processes, deterministic Lorentz stochasticity and traditional Wiener stochasticity. Further development of the work will be associated with solving optimization tasks for immune response management aimed at minimizing virus-induced damage to the organism and substantiating various therapeutic regimens used in treatment.